Hi everyone, I'm Pratik and I'm an NLP engineer at End2End. I'm going to share my insights on how to deploy serverless transformers on AWS Lambda for NLP applications. So what is deployment? All models are created to be finally be deployed into the cloud. But as we know, the truth in the industry is that 72% of the organizations that begin AI pilots in 2019 have not been able to deploy even a single application in production. There is another survey which also states that 55% of the companies have not been able to deploy ML model. So why are these data science projects failing? There are multiple reasons for it. First being delays to deployment, bad inference cost estimates, bad scaling mechanisms, train serve source differences, and data and concept drift. There is another survey around what are the different components which are difficult in the ML lifecycle. Model training is now considered to be least challenging, while model deployment is considered to be challenging by more than 50% of the companies. So this is looking like a real something that we should look into. But what stops you from deploying itself? So there, people are unable to make the CI/CD for deployment, unable to make it scalable, and it is becoming difficult to accomplish this in a low compute budget. Now, as we know, there are two major scenarios of deployment. First being the live server mechanism, where a server has to be kept running all the time, even when there is no load. This requires scaling mechanism also, and there is always some lag in the scaling. While on the other side, there are batch predictions, where you cannot serve the predictions instantly, but because of this, there will be high latency. And this also requires some mechanism either at infra level or code level for scaling. So why serverless? There are several advantages to it. First, as pay as you use. So you only will be paying when you are actually calling the model. Then it has very high scalability within seconds. And this does not require skilled DevOps engineers to actually put it into production. This brings us to the AWS Lambda, which is a proprietary service of AWS to deploy serverless applications into the cloud. Before moving forward, I would like to discuss when AWS Lambda makes sense, because there are several considerations that go into it, but let's look at some of the most important ones. So the calculation, we can compare it with an EC2, a T3 medium, which has 4 GB and 2 vCPUs and costs us 0.416 per hour. While a Lambda cost for the same 4 GB and it allocates 2 core will cost us 0.24 per hour. So this turns out to be 5.8x costlier than EC2. So from this, we can derive a rule of thumb that if the load is 1/6 parse, then AWS Lambda is going to be turn out profitable for us. But if it is more than that, then it is going to be turn out costlier than an EC2 running all the time. Again, Lambda does not have any GPU support. So this puts a constraint on us on how fast the inference can be, how big a model can be. So we found that we can get a sub-second latency for models up to bird size, which happens to be around 110 million parameters. And this is live, it's fast enough for live inferences like classification and search when the requirements are not very stringent, but just sub-second. And for certain applications like translation, it can get a bit slow and for those, we can have some batch inferencing rather than live inferencing. This slide shows us how the whole application of AWS Lambda works. So what we do is we build a container which consists of the source, the dependencies, the model itself, and operating system. We containerize it. We push it to the AWS ECR, which is Elastic Container Registry, where our container will reside. And then this container plus the environment variables we want at runtime, plus the access policy, like what AWS other services should be accessible, and runtime limits whole together forms the AWS Lambda environment. For understanding the whole thing, let's deploy a classification model on AWS Lambda from end to end. This slide shows how the source code for AWS Lambda looks like. It's pretty similar to any server code that would have written. First is a Docker file, which consists of all the installations and a line for testing our test. We have a main.py, which is like a server file, which is also called a Lambda handler file, because it contains the Lambda handler, the function that is called on calling the Lambda. Then we have our classical requirements.txt. And then we have our main source folder, which consists of all the things around the source. Main being the classifier Python file, which contains our classifier class. And it is supported by a config file and a utils file. And last but not the least, we have a test directory, which is containing a contest and a test classifier file, which is run inside the container to test out everything. Now let's have a deeper look into the classifier file. This is nothing different than our usual file. It consists of an init method, which calls this another main method to load the model. Over here, we have also a LRU cache with a max size of certain. It can be 4 or it can be 2. Depends on how much memory you want to allocate and how many different kind of models you are interested to serve. So this function takes care of loading the model. And there is another method for calling the class itself, class instance, which is like a predict method, which takes the request as the input and then does the prediction over the text inside it and returns the predictions in a particular format. This class imported in a Lambda handler file, which is called the main.py file. Over here, we import it, we create an instance of it, and there is a function called Lambda handler. It can be any name. The name does not matter, but what is important, it's called a Lambda handler, and it takes event and context. And inside it, we have the instance, which is called, and it is passed the event. The context is of no importance to us right now, but the event is basically the request, which would we have in a normal server scenario. And then we make the predictions. Inside the Docker file, it is again like a very standard Docker file where we have the environment variables, we have the requirements installation, we have a separate line for PyTorch installation because it's a CPU and we want just the CPU code for it. So we are not doing pip install torch because that installs the whole GPU version, which turns out to be 700 MB, while this one is just 150 MB. And then we run the test to confirm everything. And there is a one special line inside it for changing the mode of reading of the cache directory of the transformers. This is very important. Without this, your Lambda would not work. For saving the container in the AWS, we have to create a ECR registry where our container is pushed. And this is how it looks like with the tag latest. And usually any bird size model container with PyTorch will be around 1.5 GB. Now moving forward, we'll look at the CI/CD workflow using the GitHub action. It is super simple and it consists of some steps. First is that we have a trigger mechanism that it is triggered when a pull request is created targeting the master. And it also needs to have some changes in a directory. So we have defined that only when changes are happening to the source inside the classification, only then this workflow is triggered. So this is specifically to the classification monorepo. In this, we have the first step is about setting the directory. So we are setting the classification directory as a root path. Inside it, then there's the first step is about checking out the repository itself. And then we are building the container with the tag of latest. So this classification is same as the ECR registry name, and the tag is the latest. While we are doing that, all those installation and tests will run. If everything has succeeded, then the next step will be running. This is about setting up the AWS credentials. And then we'll pushing the container to that ECR registry. And this step takes care of that. And then after all of that is done, we want to update the Lambda function with the latest code. So this command line actually does that. For the first time, you will not be able to have a AWS Lambda function, because in order to have it, we need to have the container, and the container is not there unless it is pushed. So we need to actually create a Lambda function manually. And then inside it, we need to set up the configuration, which consists of only a few things, which is memory, how much memory we want it to use. We will require at least some minimal memory to load the model and make the inferencing. And we need to have a decent timeout so that the inferencing can take place. First inferencing will take a lot of time because the model is getting loaded into the memory, but the rest of the calls will be very fast. We also have another settings around environment variables and some VPC settings, which you can do if you are interested. After the container is updated in the Lambda function, we can test it out in the console itself. They have this feature where you can put the request, call it, and then test everything is working fine. Now our Lambda is completely ready to be exposed via an API. And for that, we can go to the API gateway and set up a simple path. It can be any path right now because we are not using the path as such in our way of calling the different functions in the Lambda. So I've just set up this simple path called classify just for verbosity. And once this is deployed, then you can call it from the postman as we are calling any other separate servers. We have to put the URL, we have the request, and we can get the response. As we can see, the response is sub-second. It is taking 358 milliseconds to process 3 text. And I would say it's decently fast for most of the applications. And this was high only because we are calling it from India and the Lambda function is in US. Otherwise, there'll be reduction of almost 200 milliseconds. And so I feel it's pretty fast. Although it completely depends on how long the text is, because transformers are quadratic, and also the size of the models. Now let's discuss some practical considerations around Lambdas. So there is a thing called versioning of the Lambdas itself, like we version other services. So there are two ways around it, that we can publish versions in the Lambda console itself. There is a feature inside it, but we found it to be a bit cumbersome to work around. So instead of that, what we do is we have two separate Lambdas for the same thing. First is the classification staging Lambda. It's named like this. It's a convention. And it will have an environment variable of staging so that we can control everything around it, the reading and writing from database and S3 files. And the production Lambda function is named like this without any staging or production name inside it, just classification, and it has set the environment as production. Although you can have any naming convention for yourself. So first we push the container to the staging environment, we test out everything, and after we are sure, we update it into the environment production. Then we have the Lambda memory consideration. This is very important. We need to know that Lambda allocates memory linearly up to 6 vCPUs, and maximum memory that can be allocated is 10 GB. So it allocates 1 core for every increase in 1667 MB of RAM. So ideally, we would like to have as much memory as we can and use up all the cores also using multiprocessing, but we are not able to make it work for our use case of using the transformers. So we do not allocate a full memory. We are just using one process. And for bird size model, we found that 2 GB of RAM is enough. There is limitation comes from the multiprocessing pool that is disabled in the AWS Lambda. They have some articles on workaround on it, but we were not able to make it work. Now we can tune the Lambda memory either manually by trying out a few requests and then checking the response, doing the calculations manually, or there is a tool for it which will actually do this exactly and give you this chart, and from that you can decide like, okay, what memory you want to allocate to that particular Lambda. Now there are some runtime limitation and consequences that you should be aware of, and when you're working with AWS Lambda. First is that there is a warm-up time. Like any other server, there will be a warm-up time every time that you have to start the container, you have to load the model. So any concurrency that is increasing will have come up with this limits that every new concurrent execution of Lambda will have this lag. And we found that it takes like around 6 seconds to start the container. like a new Lambda instance, and 4 seconds to load up the model into the memory. So first call is slow, but later everything will be fast. Next, there is a runtime write limit that you can write only 512 MB in the temp directory. You cannot write anywhere else, and the size is not changeable. So you cannot just keep on writing models to the directory of temp while in the runtime, because as you know that bird size models are around 450 MB. So you can only like write one, and maybe if you're interested, you have to clean it up and then write, and so it gets messy. Then we have the runtime memory limit. It can go up to 10 GB, as I was discussing earlier. Next, we have the function timeout of 15 minutes. So any batch processing which is heavy and running for a lot of time, it cannot exceed 15 minutes or it will like shut up. Then we have the container size limit, which can go up to 10 GBs. So we cannot put up a lot of models inside one container itself. Last, we have the concurrency limit that it varies from region to region, and it can go from up to 3000 only. So if you are dealing with some very heavy scenario, then maybe this is not the right thing for you to do. There are also some considerations around multi-tenant design, that if you are interested in loading lot of models at the runtime, then the best solution around this is to have a EFS attached to it, so that you escape the runtime storage limit and you can have as many models as you want for your runtime. There's also a concept called fat lambda, where you can have a lot of slash paths in the API gateway. So you can call different functions, different methods inside the source of AWS Lambda. Like you want to serve a lot of different models from one Lambda, you can do this, and you will be having this path in this resource of the event, and you can use its value to direct the function call. There is also a framework called Lambda REST, which will do all this for you. Some more practical considerations, that if you want to keep the Lambda warm, you can have an event-based event that keeps triggering the Lambda every few minutes. We know that it times out after 15 minutes. So we can have a event that is triggered less than that, which will keep the Lambda warm all the time. So you would not have to worry about the warm condition except for the first call. Then, as I was showing earlier, you have to tune the Lambda memory for optimal cost. You also have to apply for higher concurrency limit in advance, because if there is some situation where suddenly a lot of load comes and you do not have that limit, you will face issues and there will be a lot of problems. Also, you need to set the concurrency per function to a certain value. Otherwise, sometimes one calling of function will block all other Lambda function, because this limit is global per account. So if something is getting called a lot, then it will eat up all your concurrency limit. Then we have the LRU cache mechanism to avoid hitting the memory limit. Last is that we have to optimize the batch size for inference speed, because we know that we are interested in certain inference time, and the larger the batch size, the slower it will be. Also, it's CPU inference, so it is slower than what you would ideally want. This brings us to the conclusion that, to summarize, Lambda is super user friendly. In our experience, we found it that we can set up a service very quickly in just like a few days. I would say anybody can get it ready in just 2 days. It scales very quickly and you do not have to worry about it. It's also excellent for batch as well as API scenarios. You can use it in both the scenarios, except when the load is more than 1/6 sparsity. Otherwise, you are paying more for it. It can serve bird-sized transformers with sub-second latency, which is, I think, in my opinion, the most occurrent scenario in the industry right now. It is great for sparse loads and does not require any MLOps experience. Anybody can get started with this. So I highly recommend for those teams which are full stack teams and are looking to get started quickly on deploying the models for certain scenarios. You can find this deck at this bit.ly link. It will always be available. If you are interested to probe more around this and deploy your own serverless application of transformer for NLP into the cloud, why not check out my link where we are putting up all the different kind of pipelines of Hugging Face as well as sentence transformers encoding. And it will be very easy for you to get started with this. So thanks for coming. I hope you enjoyed the talk. In case you are interested to connect with me, I am always posting something interesting on my LinkedIn. So let's connect and have a chat. For more reading, you can go through these links where you can find more information around the limits around the AWS Lambda for your application. Thank you.